Hello everyone, welcome to today's session on one of the most fundamental chapters in organic chemistry, hydrocarbons. Today we are going to master the art of classification and the systematic way of naming these molecules using IUPAC nomenclature. I am Dr. Sankar from SS Academy and let me dive into world of carbon and hydrogen. So, what exactly are hydrocarbons? As the name suggests, they are compounds made up of entirely of hydrogen and carbon atoms. So that's why it is hydrocarbon. But why are we studying them? Well, hydrocarbons are the literal fuel of our world. They power our kitchens through LPG, our cars through petrol, and our industries through CNG. Beyond energy, they are the starting materials for almost everything you use, from the plastic bottle on your desk to the medicines in your cabinet. To study them easily, we classify hydrocarbons based on their bonds. First, we have saturated hydrocarbons like alkanes, which only have single bonds. Then we have unsaturated hydrocarbons. These are the ones with extra energy stored in the double or triple bonds known as alkene or alkynes. Finally, we have aromatic hydrocarbons, which are special ring-shaped molecules like benzene that have a unique stable personality. Let's start with alkane. These follow the general formula CnH2n plus 2. In these molecules, every carbon atom is sp3 hybridized, giving them a sturdy tetrahedral shape. Because they only have single sigma bonds, they are very stable. You will recognize them by the suffix ane, like methane, ethane, propane. Naming alkanes is like following a recipe. First, find the longest continuous carbon chain, that is your parent. Next, number the chain starting from the end closest to a branch. So that is very important. Identify your side guest or substituent like methyl or ethyl groups and give them a number based on where they sit. For example, if you have 4 carbon chain with a methyl group on the second carbon, therefore the parent chain has 4 carbon, it is butane. The methyl group sit on the second position, therefore it is called as 2-methyl butane. Did you know two molecules can have the same parts but a different shape? This is called structural isomerism. Iso means same. Take an example, butane. It can be a straight 4 carbon line with which we call as normal butane, N-butane, or it can be 3 carbon chain with a branch called isobutane. As the number of carbon grows, the number of possible shapes or isomers increases rapidly. Not all carbons in a chain are equal. We classify them by how many neighbors they have. A primary carbon is only attached to one another carbon. The secondary carbon is attached to 2 carbons. A tertiary carbon attached to 3 carbons. And a quaternary carbon is like a social butterfly attached to 4 other carbons. It is clearly shown in the presentation with colors are different to visualize easily. Knowing this helps us predict how a molecule will react in a chemical test. Now let us move to the unsaturated family. Alkenes have at least one C double bond C and follow the formula CnH2n. So remember, alkanes have the formula CnH2n plus 2. So if you remove 2 hydrogen from that alkanes, it becomes alkenes. So that is how the 1 pi bond is added to the alkanes to become alkenes. Because of the double bond, the carbons are sp2 hybridized, making the molecule flat or trigonal planar. We change the suffix from an to ene, as seen in ethene and propene. When naming alkenes, the double bond is the star of the show. Your longest chain must include the double bond, and you must number the chain to give the double bond the lowest possible number. If the bond starts at the carbon 2 in a 4-carbon chain, then the name is 2-butene or but-2-ene. Both are correct. Alkenes are even more diverse than alkanes. They show chain and position isomerism, but they also show geometrical isomerism. Because double bonds can't rotate, the groups get locked in place. If similar groups are in the same side, it is a cis isomerism. If they are in opposite side, it is trans. The example is given in the slide. This tiny difference can change the molecule's entire physical and chemical property. Next up are the alkynes. These have powerful triple bond and follow the formula CnH2n minus 2. Remember, the formula for alkane is CnH2n plus 2. Alkene, 2 hydrogens are removed, so therefore it becomes CnH2n. Alkyne, you remove further 2 hydrogen, therefore from alkane it becomes CnH2n minus 2. These carbons are sp hybridized, which makes the bond area perfectly straight or linear. The most famous example is ethane, commonly used in welding torches under the name acetylene. Nomenclature for alkynes follows the same logic as alkenes. The triple bond gets priority in numbering, and we use the suffix yne, ine. Interestingly, because alkynes are linear, they cannot show geometrical isomerism like alkenes do. They mostly stick to the chain and position isomerism. Let's wrap up with a quick summary. Alkanes are single bonded paraffins, alkenes are double bonded olefins, and alkynes are triple bonded. Each has its own formula, suffix and geometry. So this table is your cheat sheet for the entire chapter. The main things to remember are identify the bond type, find the longest chain and number it correctly. Mastery of these basics is your ticket to excelling in organic chemistry. Thank you for your attention, and I will see you in the next session to discuss how these hydrocarbons actually react.